Artificial intelligence can now defeat world chess champions, compose original music, identify cancerous tumors, and hold conversations that sound remarkably human. But here's the unsettling truth. AI has no brain, no neurons, no consciousness whatsoever. So how does something with no biological structure, no gray matter, no synapses firing, how does it learn to perform tasks that once defined human intelligence? The answer is stranger than you might think. To understand how AI learns, we need to strip away the science fiction and look at what's actually happening inside the machine. And it starts with a problem humans faced decades ago. In the mid-20th century, computer scientists asked a radical question. Could we build machines that improve from experience the way humans do? Not through programming every possible answer, but by learning patterns themselves. They looked to the human brain for inspiration. Your brain contains roughly 86 billion neurons, each connected to thousands of others, forming an immense network that processes information through electrical and chemical signals. When you learn something new, a face, a word, a skill, specific patterns of neurons fire together. Over time, those connections strengthen. The network physically changes. That's biological learning. Scientists wondered, could we mimic this process using mathematics? Could numbers and equations create artificial neurons that adjust their connections based on experience? The answer became the foundation of modern AI. An artificial neural network is a mathematical structure organized in layers. The input layer receives raw data, pixels of an image, words of a sentence, measurements from a sensor. The output layer produces an answer. Between input and output sit hidden layers, where the real magic happens. Each artificial neuron receives signals, performs a calculation, and passes the result forward. But here's the key. Every connection has a weight. Weights are numbers that determine how much influence one neuron has on another. At the start, these weights are random. The network's answers are nonsense. Learning means adjusting these weights until the answers become accurate. Here's where it gets fascinating. The network doesn't understand what it's doing. It uses a process called training, where it's fed thousands or millions of examples with known correct answers. Imagine teaching AI to recognize cats. You show it 10,000 images labeled cat or not cat. The network makes a guess for each image, then compares its guess to the correct label. Every wrong answer produces an error, a mathematical measure of how far off the guess was. The network's goal is simple: minimize that error. And it does this through a technique called backpropagation. Backpropagation works backward through the network. It calculates how much each weight contributed to the error, then adjusts those weights slightly to reduce the mistake next time. It's pure calculus. Each adjustment is minuscule, but the network repeats this process millions or billions of times, across millions of examples. Slowly, the weights shift into configurations that produce better answers. This is learning. The mathematical method guiding these adjustments is called gradient descent. Picture a landscape of hills and valleys where height represents error. The network rolls downhill, seeking the lowest valley, the configuration with minimum error. Here's the crucial point. The AI never understands what a cat is. It doesn't know softness, whiskers, or meowing. It simply learns that certain pixel patterns correlate with the label cat. It's pattern matching, not comprehension. As data flows through the layers, the network extracts increasingly complex features. Early layers might detect edges and colors. Middle layers recognize shapes. Deep layers identify eyes, ears, entire faces. When networks have many hidden layers, sometimes hundreds, we call it deep learning. More layers allow the network to learn more abstract, sophisticated patterns. This depth unlocked AI's recent explosion. But deep networks are hungry. They require enormous amounts of training data to adjust their millions or billions of weights accurately. Without sufficient examples, they overfit, memorizing rather than generalizing. This is why modern AI thrives in the internet age. Companies can harvest millions of images, texts, and recordings. The more diverse and plentiful the data, the better the network learns to handle new, unseen examples. Training a large AI model can require weeks on thousands of powerful processors, consuming as much electricity as a small town. Each tiny weight adjustment costs computation. Scale multiplies the cost exponentially. Once trained, the network is deployed, its weights are frozen. Now it can process new data almost instantly, recognizing faces, translating languages, recommending videos, all without further learning. It applies what it learned. Even a trained AI is making probabilistic guesses. It outputs a confidence score. This image is 97% likely a cat. High confidence doesn't mean understanding. It means the pattern strongly matches learned examples. And AI can fail in bizarre ways. Change a few pixels imperceptibly, and a cat becomes a toaster. The network has no common sense, no reasoning, no ability to say, "This makes no sense." It only knows patterns. Worse, if training data contains biases, racial, gender, cultural, the network learns those biases as patterns. AI doesn't question its data. It mirrors it. Garbage in, biased patterns out. Some AI learns differently through reinforcement. Instead of labeled examples, it tries actions in an environment and receives rewards or penalties. Over millions of trials, it learns which actions maximize reward. This is how AI mastered Go, chess, and video games, playing against itself billions of times, learning strategies no human taught it. The reward signal guides learning instead of labeled data. But whether supervised or reinforced, the AI never becomes conscious. It doesn't feel victory or frustration. It adjusts numbers to optimize an objective function. The appearance of intelligence is an illusion we project onto math. Recent breakthroughs like transformers, the architecture behind ChatGPT, learn relationships between words across entire sentences. They predict the next word by weighing context. Same principle. Weights, data, gradients, scaled up massively. Modern language models have hundreds of billions of parameters, weights to adjust. Trained on vast swaths of internet text, they generate eerily human-like responses. But still, pattern matching, not understanding. When AI writes a poem or answers a question, it's predicting statistically likely sequences of words based on patterns in its training data. It's sophisticated autocomplete, not creativity or comprehension. Here's the answer. AI learns by adjusting millions of numerical weights through repeated exposure to data and mathematical optimization. It's calculus, statistics, and brute force computation. Not magic, not consciousness, not understanding. What we call artificial intelligence is mathematics mimicking the results of intelligence without possessing it. The machine learns patterns, not meaning. It optimizes functions, not ideas. It's a mirror, not a mind. If you want to understand the systems reshaping our world, not the hype, but the mechanisms, subscribe to LlamaX. We explain how things actually work. Thanks for watching.